This is lab number 2, which is charge tape, which is a continuation of the first lab of lines of charge. So the purpose of this experiment is to compare the electric forces of point charges from the first lab and to this one, which is considering lines of charge, and determine the charge of each floating tape. So the materials that we use from this is the results from our last lab, those variables there, and this one for the computer for GlowScript for this one. So results of this lab is the charge of each tape on that first lab was 1.63 times 10 to negative 8 coulombs. In the second lab here, I found that a little highlight is that it's about 2.10 times 10 to negative 8 coulombs. So the fundamental principles for this lab is going to be very similar to the one last week, and it's going to be on Newton's second law, which states that a system's change in momentum is proportional to its acceleration inversely to mass. We are going to be taking advantage of the fact that F net is going to be 0 since the floating tape is at equilibrium. For the two forces in this equation is going to be the gravitational force, which is the attractive force between two objects of mass. So we see that F of g is going to be equal to mass times gravity, and in this case we're going to be equaling it to essentially Coulomb's law, or the force between two electric charges. In the purple here, we find that was the equation that we used for last lab. But for this week, we're going to be using a more sophisticated model and using the electric force of a rod in order to take that tape and to get a better view of what the electric charge would be, or electric force. So the observed model is going to be the same thing as last week. It's going to be the position of the tape B and the tape A, and then we're going to be able to float tape B as it is our system, and the surrounding is going to be tape A and everything else, and the distance between them is about 0.02 meters. So the calculations and results from lab 1, we found that the tape mass, which is 2 times 10 to negative 4 kilograms. We found the tape length and width, and we found the charge and also how many electrons it lost. So for this lab, for our computational model, we're going to be putting our input variables, which is the mass of one tape, which we found in kilograms, and our Q, which we calculated from our previous equation, and inputting R and L in order to solve for Q, for the electric force. And then we also use the length of the tape and the distance between the two tapes in this equation. So these are two functions which create the electric field and the line of charge that we're going to be using. The line charge function is one that's going to break the line of charge into discrete point charges, which each of them has Q over N. The purpose of this is that as it approaches infinity of the number of segments, it's going to be similar to a long continuous rod. So the results of our lab after running our code is that we see that the magnitude of electric force of 1.74 times 10 to negative 3 and gravitational force of 1.96 times 10 to negative 3 shows that they're very similar here. And this should be true because they are at equilibrium. They are slightly different though, as you can tell. This is because of our assumptions and possible errors in our lab. So this doesn't take into account air resistance or friction, and the measuring of the tape distances, as mentioned in the previous lab, they're pretty much approximated, and so some of this could just be human error. Similarly, we assume that this charge is uniformly distributed and that each tape contains the same charge. So, or what if and why is, what if the tape was a point charge, and why do these estimates differ, and which is closer to the real value? What if this tape was a point charge is something that we discussed in the first lab, which we have our Q, which is 1.63 times 10 to negative 8. We find that it's not very different, but it's slightly different than what we get in lab 2, which is 2.1 times 10 to negative 8. These estimates are different because they're calculated in different ways, one of them being treating it as a point and one of them being treating as a line. And so this uses in the real world, it is probably most likely closer to the real value of lab 2 because the real world definitely does not treat the length of a tape as a point. Instead, will most likely take it as a very uniform, not a uniform, but a line of charge. Thank you for watching.